Hello, this is Mr. Huebner, and this video I'm going to be working on the stratigraphy project just as a model or an example of how you would complete this yourself. So, right here is the Google Doc with the stratigraphy project. I found this from NSTA. They it's a college level assignment. I kind of scaled it back, modified it to work for to fit more what we are doing. But essentially, what we are looking at is we are combining all of the concepts that we've learned with relative dating and absolute dating, stratigraphy, and we are, instead of taking a paper test, creating a unique project based off of your own imagination. If you want to be more realistic, you can. If you want to be more on the fantasy side, using the concepts of stratigraphy and all of the unconformities, you can do that. You have that liberty. So, one of the reasons we are learning how scientists know the history of life on Earth is to promote problem solving and critical thinking skills. So there's a graphing component to this, which is, I personally think that's fun. So there's multiple requirements. Let's see, there's 1, 2, 3, 4, 5 different requirements. Starting on the first one, it says students will create at least one fictional rock layer that demonstrate the following. It says 3 suggested. I mean, if you want to do 3 of them, 2 of them, and kind of have them separate from one another, that would be simpler for you to do. You can do that. Or you can have one rock layer with everything on it, everything on just one sheet of paper. And that would be fine also. However you want to go about it, I am fine with. Alright, so what we got? Requirement 1, we have igneous rock, metamorphic rock, various sedimentary rock, cross-cutting, inclusions, superposition, a whole bunch of stuff that we need to add. So let me plop this up right here. This is kind of annoying. Yeah. What I'll do is, I should use a straight edge. Let me find a straight edge real quick. Found my straight edge. Goes to a little wooden train here. Alright. And I'm going to go off making the straight edge. There we go. Look at that. And got a whole bunch of things. I'm just going to put a little line right there. Got some line right there. There's another line. Alright, so what I did right here, I'm going to label them. I'm just going to do A, B, C, D. So we'll call this one A, B, and C. And what this right here is superposition. So I'm going to write superposition. That's one word, not supposed to be a space there. So superposition is where the oldest layers are laid first, and then new ones are laid on top of it. And what we also have going on right here is, you got it, original horizontality. So originally, the layers are laid horizontally. So we'll say this is original horizontality. Alright, there's things like cross-cutting and inclusions that we got to add. So why don't we have I can put big chunks of older rock in newer rock. So it must have been some volcanic activity. We're going to label these B. So what could have happened is a number of different things. We could have had a large layer B, and then a bunch of it get eroded, except for maybe some of these chunks for whatever happened. Maybe it was a river basin or a shallow ocean that developed here, but not over here, eroding this less. And then you had an area of deposition where layer C was then layered, and you have what we have considered to be inclusions. You got older rock caught in newer rock. You could also have some situations where there's newer rock caught in older rock. So that's inclusions. Alright, so another thing we need to do is like cross-cutting. So how are we going to do that? Cross-cutting. So I was using my pen, which you can't erase. So I don't know, you could either color it to try to hide any mistakes, or what we could pretend is that the batholith, or the section of hot magma that is the driving engine behind volcanic eruptions, is over here off the page. And it's shooting up what we call a dike, or a vent of hot magma that then shoots out in a volcanic eruption. And so that vent is coming right here. And let's say that this is the top. We got right here, it's a nice little top. Oh, and I did it again. Well, actually, no, we can make this work. Alright, and we'll call this the last layer. That's the most recent layer that's currently either being deposited or eroded away. And right here, this was cross-cutting, we're going to call that. Cross-cutting, that's new rock. So all of this rock layer was laid first. And this is the most recent one. So I'm not sure how many layers I'm going to have. Let's double check to see everything we need. First of all, oh, there's igneous, metamorphic, very sedimentary rock, cross-cutting inclusions. We got those two. Superposition, lateral continuity. Oh, shoot. We forgot to do lateral continuity. So why don't we add something like that? And it could be, let's see. Alright, I got it for us. So let's just say we had kind of a small valley because there was a river here at one time. And this is cross-cutting, so this is newer. And then the next layer, and then we got this layer right here like that. Alright, so what we got this is lateral continuity, meaning on one side of a valley or canyon to the other, you can see there's continuity of layers. Alright, so this isn't necessarily the best example of it. I needed to erase this. So a really good example would be to show lateral continuity at the surface, saying that we have currently a nice new river flowing through, and let's say this is A, and this is B, and this is C. A continues on across the valley. B continues on across the valley or the canyon, and that's lateral continuity. And we're kind of seeing that here, lateral continuity. If you were to cut a section out, this section would continue across here. It's the same thing. This is how it would look like if it was underground. At one time we had a river flowing, but then that river dried up and went away, and it became an area of deposition and new sediment formed. You could definitely have a situation like that, but again, the most iconic, easiest one to identify and see is the ones that are currently exposed at the bottom of canyons or valleys like this. Alright. But we could call this lateral continuity. Alright. What other ones? We need to show metamorphic rock, igneous rock. This is technically igneous because we're saying that it's magma that came across. That's igneous rock. Most of it's going to be sedimentary. Sedimentary rock, because it's broken up, weathered away, transported, and deposited to form new rock via diagenesis, most likely through compression and the weight of layers that come after. Metamorphic rock, you could say layer A is metamorphic because through all of the intense pressure caused by the weight of all these layers, it gained enough heat that it metamorphosed into metamorphic rock. That might be the easiest. Just put your bottom layer as metamorphic rock. Metamorphic rock. That's the most common type of metamorphic rock. You could say that there's some metamorphic rock along the igneous, because the igneous rock was so hot that it did transform some of the surrounding sedimentary rock. It's metamorphic, so that would be called contact metamorphism. You could say that there's just some metamorphic rock hanging around right over here because during that point in time there's significant geologic activity that increased the amount of pressure and temperature, therefore metamorphosing that rock in that area. So, yeah, different spots where you can put metamorphic rock, but you need to identify that into your story in one of the other parts that we will get to. Alright, so continuing on, we got all three types of rock: cross-cutting, inclusion, superposition, lateral continuity, original horizontality. We just have disconformity, nonconformity, and angular unconformity. So, let's see. Why don't we do disconformity first? So, disconformity is where you have a missing layer. Totally missing. That's where it can be hard to show. So what we could do, instead, we got A, B, C. We got a couple of layers, right? So we got A, B, C. Let's say missing layer is layer D. It's gone. So after D comes E. Why don't we say there's two missing layers? So we got A, B, C, D, E. And then this one's F, G, A, B, C, D, E, F, G. So that means you might want to identify the layer a little bit differently, and then you can label it as a disconformity. Because what's happening is layer D and E are totally missing, and I wasn't showing the video. I apologize. What I was showing was right here, we got layer F and G. It was after C, we should have D and then E, but they were missing. So, and I gave it a little extra squiggle, and I'm calling that a disconformity because we're missing layers D and E, disconformity. Then we have a nonconformity. Nonconformity is a separation between two different types of rock, either sedimentary and igneous or sedimentary and metamorphic. So you could say that we got a nonconformity right here between igneous and a sedimentary rock, or you could say there's a nonconformity here between the metamorphic rock and the sedimentary rock. So we'll call this a nonconformity. All right, nonconformity. And then the last one is angular unconformity. All right, so drawing the angular unconformity. Let's see how we're going to do that. Let's keep it simple. Do this, and then we're going to make them at an angle. Alright, I would highly recommend making a rough draft. Like, I'm going to have to redo this to make it look prettier. We'll call this angular unconformity. And this line right here we're trying to get rid of. Technically this isn't the most realistic thing. If I were to do it over again, I would put the disconformity right here, because that would allow things to make a little bit more sense. Typically if you come across an area of angular unconformity, most of the rock is going to be at an angle, because you got some weird shifting that can go on through plate tectonics, and it goes fairly deep typically. So is it realistic to put all of these concepts onto one picture? The answer is no, not really. So it's not going to be totally accurate unless you have two different pictures, like it was recommended, or three of them. Then, and one of them can be an angular unconformity, and that would be a little bit more realistic. But I'm not going to be too picky. If you have it something like this, that's fine. Just know that you're never going to see something that looks exactly like that in the real world. Alright, so let's just label them. We got G, we'll call this one H, F, oh my gosh, what's the alphabet? A, B, C, D, E, F, G, H, I, oh my gosh, I, J, J, K, we'll call this one L, put a little G right there, M, N, O, but then this last layer comes before this. So L, M, N, O, P, and this one is Q. Whew, there we go. We got all the layers, we got all the concepts, and I think that's it for the first part. There it is. Got them. What we have to do now is requirement 2. Students must include at least 3 types of fossils that fit into their fictional rock layers. So what I mean about 3 types of fossils is you got to pick 3 animals of your choice. If you want to go outside the animal kingdom and do bacteria, you can go outside the animal kingdom and do bacteria. That's fine. So any type of organisms I should specify. And it's going to relate to a story, because in requirement 3, students must interpret the rock layers and where the fossils are located and come up with a chronological story with explanations. That's where it gets fun. All right. Okay, so I just thought of 3 fossils, and I was debating, should I go fictional fantasy or should I go realism? I figure I'll just go realistic. So one of my fossils is going to be a trilobite. I'm going to put the trilobite right here. I'm not that great at art. Let me show you what I'm doing. I just put a little trilobite there and there. And because it's not that good, I'm going to make a key so that other people can understand what the heck am I even drawing. Alright, so this is trilobite. Trilobite. And you got to put them in a formation in a way that allows you to tell a geologic story. So let's see, I'm going to put whoa. What does it say right there? Metamorphic rock. Layer A is metamorphic rock. Are there any fossils found in metamorphic or igneous rock? Absolutely not. No. Fossils are only found in sedimentary rock. We'll just call that a little rock blemish. No fossil there. Let's put it up here. Look at all these fossils. Alright. I got 1, 2, 3, 4, 1, 2, 3, 4, so pretty stable population of trilobites. But then we hit this disconformity area, and I'm not going to put any more trilobites because I'm going to call that an extinction event that happened there. And it doesn't have to be a worldwide extinction event, it just could be a regional extinction event. And I think it's going to be caused by the area drying up. So at one time, this was an ocean because it was an ocean dwelling area, but then he had uplift and it rose above sea level, and so they had to move out or die. So there's not going to be any more trilobites after that because now it's above the sea, this area. Kind of in what Wisconsin in the Devonian time period, all the number one fossil that you find is a seashell or a trilobite in Wisconsin rock, because it's from the Devonian period, which would suggest that during that time period Wisconsin was under water. Fun fact. So next I'm just going to do like a dinosaur. Let's see. Little dinosaurs decided to kind of walk on here. That's a dinosaur foot. That's what I'm going to call a dinosaur foot. So why don't we say that, and we'll say that's dinosaur. Dinosaur. Yeah. Okay. And we'll just put one fossil, but then here we'll put a bunch of them. Put like 2 of them. Just a little bit, and then we'll put one here. We'll do another one like we'll do elephant. There we go, elephant. That's an elephant. We'll put a little eye there so we know that's an eye. There, that's my elephant. And we'll do elephant. And then we got I should have done a better, easier symbol. This is such a hard thing to draw. Okay, those are elephants. Huh. That's an elephant. Alright. There we go. I'll put a person here. No, I'll put a person here. I'm just going to do 4 fossils. Just to drive home a little point. I mean, you just need to do 3, but it's so much fun. I'm going to do 4. If you want to do 4, you can. Alright. There we go. So I just nailed part 2. And going to part 3, we got to make a story now. Okay, so here's the story. Wait a minute. I think I may be forgetting something. Students must date their rocks millions of years ago. Alright, so millions of years ago. That's at the very least. You got to date them millions of years ago. And then it says to explain what type of absolute dating they are using to date their rocks and create a diagram or visual. So typically it's uranium-238 you use. Breaks down to form lead-206 and has a half-life of 4.5 billion years. For what we're doing here virtually, as long as you just say utilizing uranium-238 to do absolute dating, we have identified our rocks to be this many years old. So we'll put a little dash. Let me show you what I'm doing here. Okay, so let's just say that this is 500 millions of years ago. MYA. MYA means millions of years ago. And then we'll call this one 400 millions of years ago. And this one will be 3. Alright, so I had to splice the video because I ran out of some space, but here we are continuing on. I did the whole thing and noticed it wasn't recording, so here it is a second time. So I'm going to tell the story. Part 1 was we are writing all the different rock layers, igneous rock, cross-cutting, all this different concepts of stratigraphy. Part 2 is making up 3 fossils, either realistic or fictitious, and placing them in a way that you can kind of create a story in your head, or writing. And because part 3 is writing the absolute dates, so I got 500 million years, 400, 300, so on, and this is absolute dating utilizing uranium-238. That's as much as you have to go for that one. If you want to go for some extra credit bonus, you can do the rest that's written down in that section. And just to make sure I'm saying it right, we got part 1. Computer's going slow. Part 2 is talking about the fossils. Okay, part 3 is interpreting it. You might need the help of part 4, which is stating the absolute dates right here to kind of help your wording a little bit. So I would do part 4 first and then part 3. I need to switch those on the rubric. But part 3 is telling the story. So let me do an example of my story in my little fictitious universe that's based off of realism. 500 million years ago, we don't know what happened. The reason being is because over time, we had layers build up, which caused a lot of weight and pressure and increased temperature on that bottom layer, metamorphosizing it, creating metamorphic rock, disintegrating the fossils. So there are no fossils here. Metamorphic rock. We have a nonconformity, which is a division between one type of rock and another type of rock, metamorphic and sedimentary. Alright, so then 400 million years ago, we do know what happened. We have 3 Trilobite fossils. So this is underwater. This is nice, a little shallow sea. And we got superposition, oldest layer laid first, original horizontality. They're originally laid in a horizontal manner, the rock layers. And as we continue on another 100 million years to 300 million years ago, we still have 3 trilobites. So it's a very stable population until bammo, we have this huge division and then totally different fossils after that. Totally different. So this is a disconformity showing that we're missing a bit of history. We're missing some rock layers because we go from water animals to land animals. How could that happen? So most likely what happened was we had uplift and that shallow sea now became above sea level land. And we might have lost 10, 20 million years of information of fossil record because of erosion now that's occurring. That land is being hit by wind and breaking down. And so we lost some of that sea history. But now what happens is the environment becomes more conducive to accepting sediments. So maybe it's a desert, a sandstone being formed. And we find that there's dinosaur. So a dinosaur appears. And we find that the environment gets a little bit more tropical. There's a lot more forests, and there's more dinosaurs. They really like the tropical rainforests. But then there's a shift that happens in the earth, a bunch of seismic activity, and it causes the layers to be slanted. And actually that happened around 60 million years ago, because we still had these layers that were laid horizontally originally, but then around 60 million years ago there was a big shift. It shifted it slightly. That's what we're showing here with the angular unconformity. And the T-Rex population kind of went down but then stabilized, so maybe it's a little bit drier, but still some forests around. Until we hit 60 million years ago, that seems to be a divider line where we no longer see dinosaurs and now we see elephants. Some possible reasons that this could have happened is the environment now is a grassland. So it got even drier still. That the rainforest dried up and died, and all we have is grasslands, and the dinosaurs didn't like that. So they died out. And the elephants love grasslands, so they pop up more. And they're also not being eaten by the dinosaurs. So the elephants love it. And at about 40 million years ago, alright, so our elephant population has really been expanding. And then 20 million years ago, it decreases a little bit. And then at 10 million years ago, even more. It went from 4 to 3 to 2. And then you see between 5 and 10 million years ago, there's a little person, so people pop on the scene. And then at 0 to 5 million years ago, there's no elephants, but just people. So there's two different hypotheses of what could have happened in this little universe. We have the climate was maybe changing, getting colder, that the elephants didn't like, and they were slowly on the decline, going extinct. Or you could have a situation where you do have that, but then the introduction of the people basically accelerated that extinction. So one of the two possibilities, either just natural or accelerated by another species competing for resources or eating it as a predator. So that is the story of this. Once you have that done, you can do the last part, the fifth part, which is graphing the past. Alright, so doing the last part, graphing the past, I already have it started a little bit. Ideally I wanted, yeah, I did it wrong, but I kind of fixed it a little bit. I've got 500, 400, 300, 200, 100, and so on. That's millions of years ago, and I have that exactly based off of what I wrote here. That's where I'm getting those numbers. I'm trying to make it as proportional as I can, although it doesn't really matter too much because we're speaking in relative terms when we're talking about index fossils. So we don't need to get absolute timeline lengths. Alright, so what I'm going to do is, in this first one, I've got 1, 2, 3 trilobites and 1, 2, 3 trilobites in the 400 and 300 million years ago. So right here, I'm going to do bar graph. That's going to be way better. And there we go, that's my trilobite. And then we still had 3. There we go. Because I got 1, 2, 3, 4, 5. That's how many fossils. Alright, and that's all the point in which I have trilobites. So I'm going to have to make a key right here equals trilobites. Alright, next one, I'm going to be doing 100 million years ago, and I got 1 dinosaur and then 2. Yeah, all this is gone, so we've got 1 dinosaur and then 2 at 80 million, and then I just have 1 dinosaur at 60 and 0 at 40. So then right here, dinosaur. Alright, and then the last, or no, I got 2 more actually. There's the elephant, which is at 40. We've got 1 and 4. And then at 20, it's all the way at 4. They really like whatever's going on there. And we're going to put this equals elephant. And if we see it, we're at 4. And then at 10, it's 3. And 5, it's 2. 10, it's going to be at 3. And 5, it's going to be at 2. So it's going down. And then the last one we'll say is people. That's going to be the symbol. And at 5 we have 1, and at 0 we have 2. I'll put this at 5 so we can see it better, and this is going to be 0. So half of it is that, and then the other half is people, and oop, I made a mistake. So it's only supposed to be here. So I got half people and an elephants, and then the people increase over time. Alright, and I only have so much time on the video left, but essentially what we got going on is trilobites are going strong and consistent. Got a huge geologic change that occurs. They go extinct, and we got missing information here. It's disconformity. We lost the rock layers. And then we have dinosaurs come up. They do well and then start decreasing as the environment changes. They die out. Elephants come in. Got nice grasslands that expand. They love it. They start to decrease and decrease. And then people come on the scene. And 5 million years later, they double and the elephants are gone. That is graphing the past. So remember, there's the 5 sections. You need to have all the different stratigraphy pieces like igneous rock crust cutting, lateral continuity, and such. You need to pick at least 3 fossils, put them in a logical sequence that you can make a nice logical realistic story out of. You then have to have the absolute dating, how many million years ago, utilizing the uranium-238, and tell your story. Type it in a Google Doc, and then graph your past. That is the assignment in a nutshell. If you have questions, feel free to contact me, and we will get those answered. Thank you for watching.